Hello, let's talk a little bit about control charts. A control chart is used to document the operation of a process in order to determine whether it is continuing to operate as it has operated historically. It provides operators with a stopping rule for determining when they should let the process continue to operate and when they should stop it to investigate the reason for its unusual behavior and perhaps take remedial measures. Now, control charts are appropriate for both manufacturing and service operations. Let's come back to that point a little later. Control charts are particularly useful in minimizing type 1 and type 2 errors by operators. A type 1 error is detecting a defect that is not actually present. If an operator made a type 1 error, he or she would conclude that a process was not in control, when in fact the process was in control. On the other hand, a type 2 error is failing to detect an error that is present. If an operator made a type 2 error, he or she would conclude that the process was in control, when the process was in fact not in control. Now, let's take a look at some important fundamental concepts. So, samples of a product, say 5 boxes of a pharmaceutical or chemical compound, are taken off the filling machine line. And if we observe all of them and weight each one of them, we will observe that they vary. And this is what we call natural variation. Any process will always have natural variation. So natural causes of variation are really the design of the whole process. So in this image here, we can assume that each of these little squares represent one sample of 5 boxes of our pharmaceutical or chemical compound. Okay? Now, if we keep drawing these samples of 5 units, after a while, after we have enough samples taken from a stable process, they will form a pattern called a distribution. So the solid line in this new image represents the distribution. There are many types of distributions, including the normal, the bell-shaped distribution. But the distributions do differ in terms of the central tendency or mean, the standard deviation, also called variance, and their shape. So the central tendency, standard deviation, and shape. If only natural causes of variation are present, in other words, if only those sources of variation that are proper to a process, then the output of a process forms a distribution that is stable over time. And why do we care about that? Because if a distribution is stable over time, we can make predictions. We know how the distribution will look like, how our process will behave in the future. If assignable causes of variation are present, the process output is not stable. So what is a assignable cause of variation? Are variations that are not inherent to the process. Let's say that in the case of our process, a operator became increasingly sick throughout the shift, or a machine started going out of specs throughout a period of time. So those are things that are not natural to the process. So they are assignable. Assignable because if we go to the process, we can identify specifically what is causing that variation. So again, if assignable causes of variation are present, the process output is not stable over time, and as a consequence is not also predictable. In other words, when causes that are not an expected part of our process occur, our samples will generate unexpected distributions that vary by central tendency, standard deviation, and shape. Control charts minimize type 1 and type 2 errors by providing operators with a stopping rule. If the sample statistic falls outside the control limits, the process should be stopped and investigated. In a sense, this empowers the operators by taking their judgment out of the decision about whether or not to stop a process to investigate possible deviations from normal operations. Now let's come back here very quickly. In the beginning I mentioned that statistical process control is used in manufacturing but also in service, and in our context here in healthcare. Now the nature of the defect might be different depending on what aspect of the service we're working with. So service defect is a failure to meet customer requirements. So an example in a hospital setting would be timeliness and quickness of care, staff response to requests, and so on and so forth. Now, in order for us to monitor the central tendency of a process, we use an X-bar control chart. An X-bar control chart, for us to set up, we just needed to compute three key measures: the overall average, or the grand average, X bar bar, the upper control limit, which is calculated by the grand average or overall average, plus a factor which we call A2 multiplied by the average range, and the lower control limit, which is similar except that now we are subtracting the factor A2 multiplied by the average range from the grand mean, the overall average of samples. So this sets up the chart, and then the next step is for us to just plot the average of each sample that we collect. So in the previous example I mentioned, let's collect 5 boxes of a pharmaceutical compound and weight them. So we calculate the average and then we plot the average of that sample, and we do this over time. And very similar, we do the same for the control chart, the R control chart. But here the calculations are slightly different, of course. Instead of a grand average or overall average X bar bar, we have an R bar, which is the average of the ranges. And we have to compute our upper control limit, we multiply another factor, D4 by R bar, and to compute our lower control limit, we multiply D3 by R bar. So the terminology primer contains the values of D3, D4 for different sample sizes. Now, a good rule of thumb for analyzing a control chart is that the process means and ranges should appear to be random. If there is a pattern of any sort to them, increasing over time, decreasing over time, this indicates that there is something systematic going on with the process. If there is something systematic going on, the process should be stopped in order to determine the cause and whether it warrants remedial action. Another indication is if we observe one of our observations outside the control limits, above the upper control limit, or below the lower control limit. Those are also indication that something's going on with our process, and we have indication that the process might be out of control. So we needed to stop the process and examine what is happening, what's causing that assignable variation.